Merci beaucoup, merci beaucoup pour cette gentille présentation, François. Tout à fait. Actuellement, depuis deux ans et demi presque, je suis à comment? Oh, yeah. Since 2 years, I have been something I've been with Ericsson. I'm on leave from the CNRS, and I joined the Ericsson Research team in Massy, France, which is a relatively new team. It exists like 4 years or something. 5 years is the new R&D center in Ericsson, so it's like really fresh. This branch. I will present to you a bit the activities we're working on in the Ericsson research part, but there are also other departments that are very interesting. I can speak mostly on our team. Our title today is called Run Automation with Reinforcement Learning. And I will focus on 2 use cases that we have published. There are also other use cases that we are working on, we have also published, but I cannot present everything. The one is Mobility Robustness Optimization, and the other is multi-user MIMO frequency scheduling. So altogether, what is this about? It's about 6G. And here, this slide is the evolution of the various generations and how telecommunications were shaped over time, starting like from voice and mobile broadband, going up to the app economy on the 4G, going to 5G that we live now with digitalization everywhere. And now the 6G envisions a cyber-physical interaction of the world. So first of all, exactly as this evolution shows, the services are evolving. So we start in 5G with mobile broadband, with massive connections and with URLC, which are reliable connections. And now this grows to 5G advanced. And in the 6G, all these service types will go a step further. I don't want to go into every extension, but I want to focus here that very important aspects now are including the integrated sensing. This is very important, and we have also some works going on also with some colleagues here, and the integrated AI and compute. Those are like very important new types of service that have not been included before, as well as the ubiquitous connectivity and the immersive communications. About Ericsson, so Ericsson is a very large company, right? There are 105,000 employees, 47 R&D centers, 60,000 granted patents, and it operates in 180 countries. So about Ericsson Research, where I belong, there's around 750 researchers, 50% plus are PhD students, and we are mostly responsible for the patents, actually. And there are many research areas where Ericsson Research is involved, like radio, networks, cloud systems, AI, which has our team, hardware, security, consumer industry lab, digital representation, interaction. So as you see here, there is a bullet that is not clear if it's Germany and France, but I think let's imagine that this is France. So this is where we are. Now, also Ericsson Research has different structures, right? So, I mean, one is the AI and control, where we're working. We're working on distributed intelligence, on cognitive networks, trustworthy AI, generative AI, and AI infrastructure. So what we will be showing here is mostly control issues. So this works will belong in this. Now, first of all, now I don't want to, I think it's like, it's a seminar that will not have a completely tutorial character. So I don't want to go too much into what is reinforcement learning and what are the basics. There are 2 slides about it, but I think here we need to be a bit faster and consider some things known. So we will go mostly into the presentation of results. So why do we work with reinforcement learning and multi-agent reinforcement learning in 6G? Because actually telecom environments are dynamic and stochastic, and we can use simulators, digital twins to train online, or, for example, collect data and train offline. But then these models will be put into the deployment, and then there will be a fine tuning maybe by deployment because it needs to adapt exactly to the specific, let's say, cell, to the specific environmental reality. So what is important is that the modification of certain cell parameters will also affect the surrounding cells. So this creates, let's say, a multi-agent, multi-agentic environment. And we work also with multi-agent reinforcement learning, trying to learn to achieve optimality for all agents by individual actions. And this is basically a multi-agent cooperative scenario, because usually in telecom networks, there are these common goals. So the big challenge in general in these settings is how to optimally tune all the agents that are live in different cells, maybe, and this becomes even more difficult in dense scenarios. But okay, we said all these things, but why RL? Because if we have some, let's say, expertise in the system, like some rules that are driving, let's say, the different parameters, different run automation, then these rules, although they come from experts, they are simple. They don't know everything. They cannot adapt fully to the specific statistics and uncertainties that are living inside the cell. And so an RL agent could basically, after having some cumulative knowledge at the beginning of learning, can bridge this gap and apparently exceed what the next system can do. That is that was Chinese. Okay, that is actually adapting to the statistics and taking the real data rather than giving well established but general rules of how the system should behave. There are, of course, physical limitations, like, for example, the local perception of the global system, like the observability, limited direct communication between agents, etc. So this is like a more general framework of learning within this multi-cell, multi-agent scenarios, and why RL is good. And so within this decision-making that we need to do, like there are these fundamental things, fundamental algorithms that are actually very important to us. So if we would have small problems, which we don't, then in the single agent case, we would work with dynamic programming, approximate dynamic programming, or in a simple small problem with more than one agent, we will work with game theory. However, now we actually work with large problems, and large problems have to do with space, state space, and have to do with action space. And these are also problems that have to do with uncertainty. Things are not known, neither statistics, we just have data. And so in these large problems, in a single agent setting, we work with reinforcement learning, whereas in the multi-agent setting, we work with multi-agent reinforcement learning. So today, I will present you one and one, like let's say two aspects of these works. One will be with reinforcement learning and specifically offline reinforcement learning, which is a different category. And the other is using multi-agent reinforcement learning to solve a centralized problem, but which has some benefits. We do it with multi-agents. And we will see how this is done. So these are two use cases that we had encountered at Ericsson Research. One is the Mobility Robustness Optimization. And what is this exactly? So users are moving from one cell to the other, and there are some, let's say, thresholds that need to be tuned in order for a cell to absorb, to take over the moving user, to take over the service of the moving user. So these thresholds, until now, were rule-based, and now we're trying to find an AI way to work on them. This is a paper that I recently presented at European Wireless at Nice, very nice, Nice. And it is entitled Offline Reinforcement Learning for Mobility Robustness Optimization. So we start first with this. And the next one is the multi-user MIMO frequency. So as I said, the user is moving from one cell to the other. And then at the beginning, there is a connection established with the first cell. There is a strong signal, but maybe not strong enough from the neighboring cell. But as the user is moving, this signal becomes stronger and stronger, and then there should be a handover of the service. This is the way that things are working. This is why we now move around in the city and we will drive with our cars and we have this connectivity. Otherwise, this would not work. So this is all this technology is established technology. How this works is that you have some M serving. M is some signal that can be RSRP measurements or RSRQ measurements or others based on the specific specifications of the protocol. These are all in the standards. And then you have an M target, which is like what is not yet serving, but can be a target to hand over. Now, if we didn't have anything else, obviously, if the target becomes stronger than the service, then you hand over. But it's not so simple because you actually put two extra ingredients in it. So you put, first of all, some offsets so that you don't need to be strictly larger than the serving, but you should be offset larger than the serving one. And this offset can be positive or negative, and it's tunable. We will say why. Another aspect is the time to trigger, which means that for some specific period that is defined by the protocol, then this equality should be fulfilled so that we are sure that this is the right moment to hand over. Otherwise, it will be very unstable. And now we go into these aspects that we see in the inequality, the hysteresis. The hysteresis is just an extra small offset that says, I want you to be, during this time to trigger, to satisfy this inequality under some offset plus minus. So if you drop below, it's not so bad. If you go above, it's not so bad. But the main aspect here is the A3 offset, which is a global offset that's network-wide. So all the cell pairs in the network have this global offset, and which might be 0, for example, but it might be also -2, -1 dB. But the most important, that this is what we are interested in now here, is the cell individual source target, which means that every boundary of one cell to the other, every boundary, so a pairwise relation, will have a tunable parameter. And this tunable parameter localizes the decision so that it kind of works also as a kind of a cell shaper. So this means if you put this local cell individual offset source target as too high, you tend to keep much longer the users in your cell, because you say, even if you are larger, you have to be larger than plus, plus, plus something of the neighbor for me to hand you over. Whereas if it is small or negative, then you hand over immediately. And why do you do that? Because the cells have different shapes, because there are different, let's say, mobility patterns, different trajectories, different velocities. For example, you can be at the highway or you can be at the pedestrian area, and this cannot be tuned in the same way. Now, we have worked, this is a self-organizing network mechanism. This started in 2011, 2012. This is where the sun starts living. And here is, for example, a simulator where we see, for example, these different cell individual offset relations, local cell individual offset relations. And what is very interesting here is that we don't only care about the single cell boundary from A to B, but we can also care about the second hop boundary. And why is that? Because maybe in the second hop, we can tune very low this cell individual offset, and the user might be jumping a cell so that we avoid basically a specific handover. So basically, there is immense number of parameters. And to reduce a bit your expectations, at least at this stage of the project, we don't treat right now at this talk the multi-agents scenario. We try to see in a single agent setting if we can do something better than how things are working. Okay, so we are trying to improve over the mobility robustness optimization framework. So what is the problem when you have a wrong tuning of this parameter? You can have errors, and these come from radio link failures. That means the links are failing and you lose connectivity. So for example, you can have radio link failure too early, which means that you sent from A to B, and in B, you got an X. That means you got a radio link failure. It failed. That means it didn't connect to B. Maybe you have it too late. That means you kept the user so long in your cell that it dropped. Other things are the ping pongs. For example, that as you move slowly towards one cell, you send them to the other cell, but then it's not the right moment. So this is sent back, it's not the right moment, etc. So this can be a sequential ping pong. But even if it's successful, right? Another thing can be the short stays, which are not sequential, but we don't want them either because they are redundant. So if, for example, you have from A to B, and immediately in 1 second you go from B to C, that was not a good tuning, because you wasted 2 handovers instead of 1. Other issues is that when you go to A to B and then from B to C and you fail. And another important category is the wrong cells. That means you go from A to B, you fail, and instead of trying to reconnect to B, you reconnect to another cell, C, which means that you shouldn't be at B anyway. You should have sent the user to C. That means the tuning should have been different. So there is like a big taxonomy of issues that we use as input in order to tune this stuff. And how do we tune them currently, more or less? it is basically based on some sums. So we create an early sum, which is a linear combination of the issues associated with low tuning of the handover. This can be, for example, the too early failures, the ping pongs, etc. Why the ping pong? Because you sent them too early and then it came back. And then we also do a linear sum of the late issues, and these are compared. How are they compared? We take their difference, okay? What is the aim? The aim is to have jointly low issues. We don't want either early or late. It's not easy to have jointly low issues because when you tune the cell individual offset, the more high you go, the early issues drop, but the late issues increase. And so you see that there is a point in what touches one the other. And then since there is two monotonicities and they are going the other way around, when you add them up, this point which is touching is close to the minimizer of the two. And this is like the logic behind. So if you take the difference, you want to keep as close as possible to this, a good operation, to this tuning. This empirically minimizes the sum. It can be shown with small examples that it's not the actual minimizer, but anyway. And now how the algorithm works, like try to keep the difference E sum minus L sum within some boundaries, negative and positive, minus threshold, plus threshold. If you are lower than minus threshold, then you have more lates than early issues. So since you have more late issues than early issues, that means you keep the user too long and you need to reduce by minus 1 dB. If you are on the other way, on the other extreme, you have more early issues, then you have to increase by 1. And this is how a bit variations of this can be found in the literature. This is how more or less this SON has been working since 2012. Now, what we want now is that we want to ask, okay, if we will use the same data that we use to actually do this choice of without doing these empirical, let's say, differences and ratios, can we feed a reinforcement learning algorithm to learn the solution? And we do it for just a single cell pair at this stage. And so the actions remain +1, -1, and 0. The state is the same as before. And then we need to create a reward. And we just need to find a reward that is as equivalent as the previous one so that we don't start creating new rewards. And so the previous one was trying to minimize the sum of issues. And so that means that the reward should maximize the negative sum of issues, right? Since it's a reward. But since this is negative, and since we want also to give a bit more emphasis in the difference from one tuning to the other, we put the exponential of these issues because it keeps the convexity and like everything can work. It has the same, let's say, solution. Now, okay, let's go to online reinforcement learning. So, okay, you have your state, you have your action, you have your reward, and someone says, go, my friend, take the simulator, or the digital twin, evaluate your KPIs, take your samples, do your exploration, and things will work out. But no, because now we are in industry land. We are in real world land. What's the problem with this? It's that when you tune a parameter, in order to collect these KPIs in real world, you need 24 hours. Now, for a single sample. And in the simulator, you can simulate something less, but you still need an enormous amount of time for a single collected sample. And so you cannot just throw an online RL and say, you know, take samples, update, etc., and find the solution. So you need to go a bit differently. Either you do a faster than real-time simulator, which is now actually in the industry, people who are working on that, which makes a lot of sense. It accelerates the process, but still it's not exact. And still it's not the actual cell that you're working on. Or you go to what we call offline reinforcement learning, which has to do with collected real data that you have in your disposal. And you know, let's say, how they're operating under some what we call behavior policy. And then you try to find a better solution offline RL than the solution these policies tell you, the behavioral policies. and you don't want to do any further exploration. So it's an RL without exploration. How would a trajectory look? So it would look like this. You have, for example, a situation where you have average velocity of 120 kilometers per hour. It's a low load. And you have a specific seed, which means specific ways of trajectories. And you start by a tuning of -8. And then you have a reinforcement learning trajectory, which actually has a number of steps. Here's 17, I will tell you why. And then at every step, you take some actions based on some behavior policy. And in that case, we are increasing at every step +1, +1, +1, up to converging to -2. And this is where we stop. And basically, this is one way to tune within 17 steps. That's what we call a trajectory of the imaginative behavioral policy. This trajectory will have a sum of rewards, will be in individual reward will be the reward we described with exponential, right? So the first will be 0.92. And how do the rewards come? They come by the calculation of the late and early costs. The early from the early issues, the late from the late issues. The reward gathers everything up, and then we get this. So how do we do that? We had already, from Mobility Robustness Optimization, collected data. So there were some algorithms that were running, and we knew how these things would be tuned if it started by some position and go further. Now, we also used simulator to collect other behavior policies that was taking weeks actually to do that because of these time delays. So for specific, let's say, velocities and loads, we collected, for example, with a bit of random choices. Then we took up, like starting from a position and increasing, and starting from a position and decreasing. And I will tell you why we did that. Now, we did it because we do offline RL. And the result depends on what data set you have. What is the group of trajectories that you use to learn? And this group should contain transitions to high reward regions. And already we have the high reward regions, which are from the Mobility Robustness Optimization, the rule base that was already well working. But the thing is that you need to have differentiation inside the trajectories you have. You don't have to have only the expert policy, otherwise it would give you the same result. You need to have differentiations from other types of policies, like the up, down, the random, so that the offline RL can learn to stitch together parts of your different trajectories and to come up with a new idea, a new policy that can do something better. The problem also with the offline RL is that because you don't have the exploration, you have two problems: the state distribution shift and the action distribution shift. So the state distribution shift is when you have a data set, you have visited certain states, but your data set is limited. If you go to the real world and you start visiting states that were not in your data set, you are out of your distribution of the state. So what will the algorithm do there? No one knows, and that's the problem. That's very dangerous. And another issue, the action distribution state, is that for some state, you took actions in your behavior, in your data set, but when you're outside your data set, and you take, and you can, the algorithm can propose an action because it is a deep network. It can propose an action that has never been seen in the data set. And maybe this action that is proposed gives a prediction of the value function on the Q value that is overly optimistic. And then someone said, that's the optimal policy. But it's not, because you never tried it. You don't know if it's just the artifact of how your training has happened. And to see that, let's see this example. On the left, you have the actual Q value function that is actually the dotted one. And this is over for a specific state over different actions taken. And you see that there is only a specific action supporting your behavior policy. That means a specific part is known to you from your data, which is within these lines. But outside these lines, there is actions that you never tried. So maybe you have learned basically, you have learned a Q value critic that is being overly optimistic for actions that are outside your support. And like here, you get a naive Q function that is overshooting. And that means that based on what you see, you should take this action that's outside your action support. But this is not a reliable action. You should not do that. You don't know what it will do. And so there is this Bellman-based techniques that are called conservative Q-learning that are giving conservative approach to when you don't have actions where actions are outside your support. And so this lower bounds the Q value. And how does it do that? It just creates a new loss function. And the first part is the TD0, which basically, if you are familiar, is basically the Bellman loss, right? The loss that tries to keep you close to the Bellman equations. And the other part is the extra part, is called the action out of distribution penalty. And what does it do? It says for any state that I see, there are many actions. And for these actions, I create the sum of exponentials of the Q values. What is the Q value, the value to go that I predict? So what I'm doing first is that I am minimizing all possible actions, but then I'm maximizing, right, over the actions that I know. So this means that for the actions that I know, I want to promote them, whereas all the other actions that are not known are pushed down. And so this way, this gives the pessimism, the conservatism about actions that you have never seen, and this is how this achieves a better result. The other algorithm that we used is inspired by transformers, and it's called decision transformers. So basically, the transformers is a sequence modeling autoregressive model, which is very well known from large language models. And what it does is that it predicts tokens. Okay, and then there was like these smart guys. I really think it's Berkeley. That they said, okay, why don't we use the same thing that is predicting the next token in a language and predict the next action in a reinforcement learning setting, right? So I put behind all the states, actions, and rewards that were used up to now, spit the next action, right? But yeah, why should the next action that is pushed out should be good? Why should this action maximize? And this is a bit like the magic, because these models are goal-oriented models, and you should set a goal for the model to do something. And this goal is set by the big capital R, which is the reward to go. So it takes as input in the sequence the capital R, which is the reward to go from the specific point up to the end. But it starts also from the beginning. That means the R0, capital R, is the reward to go of the full sequence. So now if you tell to this person, we start now generating actions. I give you my state, but I give you a reward to go for the whole sequence that's really high. So now you have to know to push out actions that can reach this really high reward to go. And so you are nudging the transformer to produce actions that are maximizing the reward to go. And funnily, really funnily, because it doesn't have Bellman, it doesn't have anything, this thing works. We were really impressed. So it works because there's this attention mechanism that has learned a type of model from this data set. It has learned how one action, one state can affect the rewards. And now from the training, it does what we call stitching together. It has taken, let's say, trajectories and starts stitching them together and creating a better trajectory, a better policy. So let's go to the results. Like we simulated the setting of the handover for only a single tuning. Then we just to have a bit more data, we kind of grouped together some pairs that would behave in the same way, and then we applied the algorithm to these pairs, and these are the pairs that we believed, let's say, that they would have the same behavior. And then we tuned the time to trigger in 160 milliseconds, the hysteresis to 1 dB and the offset to 3 dB. These are a bit close to how, let's say, a very, typical cell would work. And then we have 7 base stations and 3 symmetric cells. And the cell individual offset ranges from -8 to 8 dB. It's allowed to take these extreme values. And now something technically very important is that how do we create the early and late issues, and how do we create the rewards? And that was like a very engineering task. Because, of course, when you have a radial link failure, nobody tells you, I'm an early issue or I'm a late issue. You need to somehow extract a categorization that's not machine learning. This is really engineering process of this is a late and this is an early issue. And this comes out of two signals that we receive. The one is the radio link failure type. One is called random access failure. That is a failure during the random access. The other is out of sync, that the user is out of sync. The other is the timeout on handover. And we also know at what state of the handover process the handover has failed. And so, for example, it can be before or after the measurement reporting. It can be before or after the handover command is received, etc. So depending on this, we created, let's say, categories of early and late issues, and we were able to create our reward. We trained on some velocities of mixes of 4, 50, and 120 kilometers per hour. And with specific loads, these are just low load means low load, high load. Numbers don't make very importance. And we validated on different loads and different velocities. And so here is interesting. The first thing is the collected dataset trajectories. So here is the dataset trajectory, the trajectory value, the histogram of the trajectory value. So you see that we collected trajectories that had almost from 0 until to 30. It was all this range. But of course, you know that if you have a low range of values, it's a bad trajectory because you would have a lot of issues, so you don't have a high reward, right? You have a peak on the 30, but this is an artifact. I don't want to go into these details. It's an artifact of the fact that we had short time of collection of data, and sometimes nothing happened because these are rare events. As I said, you leave them for days. So since nothing happens, the reward is maximum, right? So these are practical issues. Like it's not, it's like very engineering approach right now. So what we expect from the offline RL is to learn a policy that is good, and means that on the same situations, we want to produce high reward trajectories, right? So we applied the decision transformer, and here's what we got. So we got an histogram of rewards that was concentrated above 15. So the transformer learned to make actions that are not producing low rewards. Yeah, please. Yeah, please, yeah.
How do you compute these scores? Do you apply your new policy?
Yes, you apply your new policy in the real network. Yes.
Okay.
Yes. Yes. Exactly. Now, so did we get a better policy compared to the MRO rule-based? We did. So here are some examples. For example, when we have a high load of 0.7 and a velocity of 50 kilometers per hour, there was a better result because the final tuning at the end of the trajectory, at the end of the 10, 15 steps we did, it tuned differently than the MRO rule-based. So here, for example, instead of tuning -2, it tuned -3. This gives a reward of a 4.1% of gain, but this gain should be translated, and this we don't show here, on specific gains on early and late issues, like how much we gained. But we gained in the sum of early and late issues. And similarly, when we had, let's say, 0.4 load and 50 kilometers per hour, we tuned lower, we tuned to -4 with this offline, and we got a 6% improvement. So actually, we just had the MRO trajectories. We used some other enriched data set. We applied offline RL, and it found a better way to tune. And actually, this was confirmed also in the test scenarios that were scenarios with different velocities and different loads. And we got, again, a better tuning for example, and gains, for example, for the 25, 95 kilometers per hour velocities. Now, interestingly, the solution was stable. The solution is stable, meaning that whatever would be the beginning of the initial cell individual offset value, we would converge to the same value, more or less, plus minus. So this means that it did not, depend on the initial position. And what is very interesting is that we did it for some reward, but we can change the reward now. With the same data set, without any exploration, we can put another reward, retrain again, without any more collection of data, and get again better solution. Let's see that. So here we applied same data, alternative reward. The new reward is the previous one minus some lambda of a cost to increase too much, change too much the cell individual offset from 0. It's a new reward, right? And now you see that before it was tuned to -3 and -4, but now it is tuned to -1 and -2. So now it is more conservative in what is the landing cell individual offset. It learned to do that. And for this reward, it gives higher reward than the rule-based policy. Without any exploration, no more simulations, nothing. So yeah, so this was the first results of what we did. We saw benefits from the offline RL for a single agent. We generalized to unseen traffic. And we saw that it converges to the same solution irrespective of initialization. And we're working on the joint tuning and on user-specific, say, individual object tuning. This is something that is ongoing work. So if you have some questions, I just have 10 minutes for the next part, but it's okay. Yeah.
So did you compare offline learning versus online learning?
We can't for the moment. Because
maybe for a smaller smaller set of examples.
The problem, I mean, I would think that online RL, it could even go higher because it doesn't have all the restrictions and can explore everything.
Yes.
But to do that, you need digital twins and big simulators. We have big simulators, but fast, very fast simulators. And if you have a very fast simulator, unfortunately, you might lose in precision. So you do simplifications to make something very fast, because what happens is that you tune and then you say, I have 30 users, and they just start moving with their trajectories. And you wait for a long time until some user fails. Then you have one failure, then move again. Then some user starts ping pongs. And this happens over time. It can take hours until you collect this thing. And after it collected, it says, with this tuning, that's my KPIs. So what you're asking is for a simulator or a digital twin that can accelerate this process of evaluating the KPI.
Well, simply you collect one data set one day, you change your agent, and you get the reward the next day by collecting some more data.
Yeah, but how many months? Because this is not for, this is for any velocity, any load, any type of trajectories.
Well, that's a link to my second question. This is highly dependent on the data set you use. So
yeah, I agree. Yeah.
How can you produce a better data set for your purpose?
That's a good question. Like the data set plays an important role, but this we can go, we have some work on that. The different offline RL algorithms, they depend a lot, as you say, on the type of data set. So a different data set will work well for or conservative Q-learning. A different data set will work well on decision transformers. There are papers that have done some first studies on that, and they have been published also in ICLR. Actually, the paper's title is this question: when does decision transformer work better for offline RL, something like that? And the answer is that, for example, the offline RL for decision transformers, it needs a lot of expertise, but not so much medium or random data. But it does need that in order to be able to find something better, but not too much, because then it gets perturbed. The conservative Q-learning, on the other hand, is much more robust. And actually, the more you give medium or better coverage of data, the better it can generalize, because it uses the Bellman. The one is trying to do something more like imitation learning, like tries to mimic, whereas the other is actually trying to learn what are the good Q values, and then this is more robust to bad results. So this is a big discussion, I think. Maybe in the next 5-6 minutes, I present a bit this other work that is from last year, and we can catch up all together. So the next work is about multi-user MIMO frequency scheduling. It is In the scheduling part, we have the time domain, the frequency domain, the beamforming, the power control, the link adaptation. For the moment here, we were interested to associate users to subbands, right? We have like 10 subbands, subfrequencies, have a bunch of users that need to be scheduled, and we have to see which users go to which subband, but with the extra element of multi-user MIMO. That means that we can schedule more than one user to the same subband, because we can separate their signals with multi-user MIMO. And this makes the problem very complicated, basically. So the ML that we use ML, and why? Because there's uncertainty. We don't know the exact channels. We don't know the estimation. There are estimation errors. We don't know the user mobility. There are finite buffers. There are diverse quality of service requirements. And actually, even if this would be exactly known, that would be a very big mixed integer program. Now we want an RL and machine learning model to learn these things. And the challenges are, we have limited GPU. We have an inference time of less than 1 millisecond, because if you run frequency scheduling, this would be like really fast. And we have to find a coordination between decision dimensions. And so in this frequency scheduling part, as I said, this is a multi-user MIMO where users with orthogonal channels can share the same frequency. So we can serve more users. The non-NAI baseline is a greedy one, but can we do better? And so the problem here is combinatorial. This is the problem, because here, let's see a problem of the actions. Suppose you have 4 users and you have 2 multi-user MIMO channels. Then combinatorially, this will give 10 possible sub-actions. Now, if you go to 10 users for these 2 channels, you go to 55 sub-actions. And so the action space, you see, grows and grows and grows. So if you have 10 users and 15 subbands, you arrive at 10 to the power of 26. So you understand that this cannot be solved in a centralized manner. Okay, you need to find a way to solve this. The reward that you're trying to get is the proportional fair reward over the rates that the users are getting. We consider here, some people, like, this is basically, we consider here initially a myopic problem, like a bandit problem, but we don't solve it with bandits. We solve it with techniques from reinforcement learning, although we use a gamma equal to 0, but that allows, with a multi-agent setting, to learn good policies even for myopic settings. And we will see how. The input is the channels. We have channel estimates that might not be precise. We have buffers, and we have some other contexts, and we can also put some previous rewards that were associated. So how do you make this big combinatorial problem simple and you can solve it in such a small time? Okay, we know the deep Q learning. So this is exactly the same as before. So if you would apply, if you want to take one action, you would use this loss, and then you would have prioritized experience replay to emphasize on, samples that are improving a lot. You can use target. You can do online. So anyway, we do multi-agent, and this is like the solution that we found. One of the solutions, because there's another paper before that was doing a sequential Monte Carlo search. So we can talk about it a bit later. But what we thought was that since every subband has to decide about what users to associate, then why don't we let it decide on that, right? So this reduces the action. So that means instead of having these millions of possible actions, now every subband can have, let's say, 10 possible actions. So with these 10 possible actions, every subband will output some Q value of each of these 10 actions. And the problem is how to combine them into coordination. And this is the big problem of the centralized solution for this multi-agent problem, how to combine into coordination. So I don't want to go completely into details. I want to give more of the intuition. And since we don't have a lot of time, I think it's 54. There were 2 ways to give the coordination. The first part was that we created what we call a shared representation. So since anyway, the problem should be solved for everyone in a centralized manner, we can put all the information for all the channels, pass them through a learning, a pre-learning phase, and create a learned representation of the global situation that is then pushed inside each of the branches individually, together with their local information. That means if you know the channels at your sub-carrier, you take them, plus this learned global global information. So this is one part that the cooperation. That means we force as an input the cooperation, and then we learn the best representation that coordinates, right? So I don't know, like imagine a signal that says 15, and 15 means a specific type of association, and then when one gets 15, he says, I will do that. When the other gets 15, then I will do something else. You see what I mean? Or case 12, case 5. This is just a hard way to say. Yes, we used branching, like this called action branching, basically, that you branch for each dimension. And we use the dwelling action. The dwelling action just tries to, it's a bit of a technique that's quite established that tries to separate based on the average value to see which value action exceeds a bit the average value action. Or the anyway, this is a bit too details. I can like come back to you whenever you want. But the important thing is the shared representation in the learning. And the second part is that we need to now do something extra, which is change the loss. Now, every branch is outputting these Q values, right? But then we will take one action from every branch, and then this one action from every branch will create the final action. But then we need to find also a way to learn also from the loss. So how do we do it? We sum over all the Q values, over all the branches, and say that this sum should somehow be combined, let it learn by itself, to achieve the reward. And so this is called value decomposition, and somehow the Q values are learning to separate their importance by themselves through the loss function, on which part is giving this part to the R and which gives the other part. And so the two elements of cooperation in this multi-agent setting has been the shared representation to learn something global about the world and then feed each multi-agent. And then the second is train the Q values that are output by its agent as a sum that are trying to achieve the same global common reward. This is a multi-agent cooperative because the reward is R, is always the same, the sum of proportional fair over users. There are many other techniques that are doing loss function aggregation. This was the first one that was proposed by Google, and then there was other techniques that were called Q-mix. They used graphs also and message passing, but this was the first idea in the loss function. And so the question is, can we simplify? And then there were simplifications, like for example, we supposed, what if we put the same parameterization on every agent? Can we reduce the number of parameters? Because the more you have agents, the more you have parameters. So maybe we can use the same, let's say, machine learning model to replace everything, and then only the shared representation and the combination at the end can modify. And another interesting thing was the GNN, because in the graph neural networks, there is always a common learning network that is taking as input something and output something else. And then it learns based on neighbors. Now we consider that there is a full graph connecting all possible sub-channels. And we learned basically the shared representation from this graph that was just part of the full loop. And so after this, we applied with a CNN simulator, urban macro cell, a circle sector of radius 500. So we had like all these parameters, and then these are the results. The results are comparative to the rule-based, so more or less, let's say how this would work today. Not really, but it's a very advanced rule base that is like very demanding. And you see that you can have very strong benefits depending on the uncertainty that there is in the channel. So if you have, for example, a very higher speeds of users, then the channels are not precise, they are stale. And so you would not use this information to actually do the right multi-user MIMO. Now, with the reinforcement learning, you can reach up to 184, 187% of improvements. Other thing can be how noisy these are. So you can have basically 250% of improvements based on that. So yeah, these are a bit what I wanted to say. Yeah, and this last part is, okay, how did we achieve these results? How big were the networks? And this is in industry very important, especially now that we're talking about GPUs. And we see here the number of parameters involved in every type of architecture. And we see that the action branching, if you just take it purely, it's immense, like it's 10 to the power of 6, but it has this smallest inference time that we keep it as reference. But now, if you go to unibranch, because you use the same network, you reduce, of course, the parameters, and you get almost the same inference, but still it's 10 to the power of 6. If you go to graph neural network, and this was very interesting, this is a very powerful tool. It can summarize very well the interactions between other, so it will work very well as a shared representation. And this had only 10 to the power of 4 parameters. And that was actually, let's say, the cheapest solution that we found, and with an inference type of 1.76 compared to the action branching. And what we call alpha 0 was in another paper of the same company from our group in Sweden, where they were using Monte Carlo tree search with sequential actions, first the first subcarrier, the second, the third, etc. And then the inference time was 16 because they had to run for every step the algorithm to output for every subcarrier one solution. And this also happened to the power of 4, but the inference time was very expensive. And so with the graph neural network solution, the shared representation, we have a cheap solution in number of parameters, which has a very high inference and very good results. So yeah, this is, and also this is online adaptation. That means that now you have done this. Does it fine tune fast? Okay, you did it in your simulator, and then you go to a real scenario where, you know, velocities change or whatever. Now, since you have trained already something, with just a few samples, you can immediately converge in very small number of seconds to the best solution. This is shown by the orange curve, instead of retraining the whole thing. So this has also like this online adaptability. So with this, yeah, I conclude my talk with these 2 use cases we have worked. We're doing many other things, but yes, thank you for your attention. Please, I would be happy with questions.
Here.
Wow.
Hello. No, yeah. I have many, but I will sample one. The last slide you showed about fine tuning. So how do you fine tune? It's just a curiosity. Do you allow all the parameters to change during your training, or do you keep like some layers fixed?
We kept some layers fixed, and we changed.
Okay, so I mean, how did you?
Yeah, we just kept the last layer. I think we changed only the layers of the. We didn't change the shared representation at this stage. We changed only the how's it called, the DQN layers. But this depends. So this is like, I can add something. This is like the first work. There are some other works that we have not published, and you can also like allow the same model to learn also multiple, let's say, velocities or multiple users. So you can also have better generalization. But this was, we changed one layer and then you could
okay. And also during training, you gave to the training process different situations, and you forced some layers to remain fixed, and the last
yes and no. So there were some, but we could not at this stage of the model. That was last year that we published it. We were more limited in the number of situations that one common network could handle. But right now, with modifications that have been done, it can be much more flexible.
Okay, thank you.
I think in slide 8, you mentioned about small problems and large problems and the tool you use for them.
Here, you mean?
Yes. How do you classify problem as small or large? Is there?
Well, I mean, I would say this is a bit empirical, depending on. For example, if you have just a couple of states that you can enumerate, like 15 states, and a couple of actions you can enumerate, this is a small problem because you can write all possible combinations and find explicitly the value of every one of them. Mm-hmm. Now, in the case of the problems that I show you, especially the second one, you see that the state and the action explodes. The state is all possible channels of all possible users with all buffers and all context situations. So it was very difficult already, I didn't say this, to pre-process the input state in order to make a representation per channel that is small enough and can have a meaningful size of. So it was like quite a difficult problem, the scheduling. Mm-hmm. Each one of them had their practical difficulties, I would say. So this is why I want to present.
And also, like you are doing resource allocation, and the problems are combinatorial bin packing problems. Say.
Yeah.
So there is no guarantee of optimality. So
there is no guarantee of optimality, but there is no guarantee of solution, because your channels are so uncertain, depending on the velocity, depending on the noise that you have. You don't have this actual information. Sometimes your information you have is delayed. You don't have the exact information at the right time. So the problem comes from the nature of the problem itself, not only from the mathematical aspect. Okay. Thanks. I hope I answered. Yeah.
Any other questions? I had one on my side. So you alluded to this AlphaZero. Is it any connected to the AlphaGo things, which also use MDP and?
Exactly. Yes.
Right. So all this line of thought are variants of the AlphaGo strategy, and that's quite amazing, right?
That was a very nice work. This preceded our work because it was published earlier. It was from a colleague that actually also is in the team that worked on the second problem, and they continue also. I can give you some details about how they worked on that. So in the AlphaGo, for example, you can have a sequence of actions and states, of course, that they lead in a rollout to some result. Now, I think, if I remember correctly, the idea here was that, for example, if you have a root state at the beginning, then suppose that instead of taking turns over time, you just give an order on the subbands on how you will allocate users. And so, for example, at the beginning, you allocate always to subband 1, then to subband 2, then to subband 3, and this creates, let's say, the small game. But of course, the result is the rollout of the game on the last part, because if you just do a greedy thing at the beginning, then maybe you lose everything because your users should have been better in, let's say, some X other subband. And so here, each subband has a number of actions, which is a combination, and then you learn using the same logic actually as the AlphaZero, how to explore with a probability that, for example, if you pass through this path, then if you are not passed many times, you need to explore more there. And so you need to increase the probability of passing from there to see what happens. And so this is they have done exactly the same thing. Yeah.
I see. It's quite amazing that, I mean, because this AlphaGo was a big breakthrough, right?
Exactly, it was a big breakthrough. Yes.
And so this is really the same mechanisms.
It's really the same mechanism. Yes, it's exactly the same. Actually, they use the part of the JAX code that was available by Google to do that. They adapted JAX is the language developed by Google.
So I mean, there were really what was amazing is that it was self-trained.
Mm-hmm.
The AlphaGo was self-trained. So you gave the rules to AlphaGo.
Yeah.
And it would play better than the best Go players worldwide.
Yes, yes.
Without training.
But this you cannot do here because you don't have a very specific environment that
there are no
repeats
rules.
itself.
There are no rules.
There are no rules.
Right.
Exactly. Yeah.
Okay, but the principle, I mean, I think it was the first, if I remember well, the first
algorithm.
MDP-based algorithm which would replace, fundamentally AI-based.
Yeah.
That would only use the rules given to it to self-train.
Exactly. Yeah.
And so, okay, but here there are no rules. I mean,
here there are no rules, but maybe there are other situations that could be relevant to that. Here you just take the logic of the exploration of the trajectory.
Yeah.
That is follows the same thing as the game. Let's say the multi-sequential game. Exactly.
Okay. Yeah. Thanks a lot.
Yeah. Thank you very much for the questions.
Let's thank the speaker. There is one more question. Oh.
In MCTS, usually it's for deterministic games like chess or Go. Here you have a stochastic aspect. So how do you? I mean, it's not you, I know, but
how they did that?
How did they did that?
If I remember correctly, at every node you had a probability,
okay,
and this probability was learned through a neural network. The probability of exploration, the probability of going left or right. And I think this was like so. In the bandit case, if I remember correctly, there is this algorithm that depends on the variance.
Yes, UCB.
Yes,
UCT or UCB.
UCT. Yes, and it's exactly the same thing here. That means that the probability to go somewhere depends also on extra plus the variance that you would have because you didn't go there, and this is learned over time and it changes as you divide it by number of times you go through. This is how they did that.
Okay.
So the difference with the inference based on of this and the inference we do, and this is important. It's nice that we go into this, let's say, comparison. Is that first of all, this was. I mean, I support fully this work, although I did not get involved. It was before my time, because this work can show a better scaling practically in very big sub-channel problems, like which gets more and more difficult for there's no free lunch, right? So in the parallel setting, it gets more and more difficult when you add more than 10, or like it really you need a lot of data to do it. This seems to perform better, but the difference is that to take an inference decision, you need to run as many times as the sub-channels are there. So you multiply the time of inference by the number of sub-channels. Whereas in the case of the parallelization, the decision is immediate for all the sub-channels. And this was a bit also the motivation for us to explore this alternative approach. However, indeed, this is a valid and not only valid, this is a very well-established, let's say, solution also inside Ericsson for working on that. And you can also go to the relevant paper of the colleagues to read through. Yes, by all means.
Okay. Just a last question on the way you are working on this kind of problem. It seems that there are many tools in the literature, and at the end you have a recipe. Let's say you have action branching, you have dueling, you have transformers, and so on. And tell me if I'm wrong, but these tools are known in the literature, maybe in a different context and so on. And it seems that people working on that, they try some recipes. I try some mixture. I do a lot of simulations. Then I see it's not working. I change this. Maybe I have some intuition or something like that. Is it like this, or do you have a more formal way of doing?
Yeah, I guess this also goes to the question on the first part, where we'll use decision transformers. And I would say that the more you dive into these tools, which we say are tools, and the more you understand that finally there are rules, empirical rules, when they work better and why they work better. In this case, there was, for example, a necessity from the mathematical point of view to learn a big action problem, which is combinatorial. So you need to find a way how to do it. And either you will solve it sequentially, as there was the AlphaGo, or you would solve it in parallel, and that was a multi-agent in general. The question then is, how do you combine multi-agents? And then, for example, the value decomposition or the QMix are established ways to make multi-agents combine, or for example, the EPO, the MAPO, or whatever. Now, since we had a centralized problem, we did not need to treat these agents as completely on their own. So we could add some extra global signals. And indeed, yes, we found in the literature that this global signal can be either the GNN or this general representation that is called action branching. But I think it has a logic, all this thing. Now, indeed, some things will work or will not work, also because some papers are working well in the use cases they show in the their performance, but they will not work outside their comfort zone. And we encountered also these things empirically, yes. Okay. So you debug also a bit the available literature by, I think everyone who is working a bit on machine learning tools kind of understands this thing, and that's why also the question, I guess, right? So we didn't know also if it would be Q conservative Q learning or decision transformer that will work better, because people promise stuff in the papers, and then you see that there's a sequence of papers after these papers that are trying to understand what these people are saying, and they're comparing, but then they are comparing with these specific established data sets, but these data sets are not stochastic, for example, and then okay, yes, you had deterministic data sets with different initial position, but this is not the telecom world. So even when you read the papers after the papers, you don't know if this will work in your case. So yes, you have trial and error.
Okay, thank you.
Yeah.
Okay, so let's thank you.
Thank you for having me.